Hi, as our main reference, I have referred to Federer's book and Evans and Gary EP for proofs of the Coarea Formula. But there's also this very important, beautiful note by Nicolaescu, and I want to go over it because it's a good reference, and I want to point out some points about these notes. Secondly, there are generalizations of the Coarea Formula for other contexts. For example, for maps between manifolds, as you see here on page 13, and even for maps that are defined between rectifiable sets, which are geometric measure theory creatures that look like manifolds, but only roughly. These notes are quite interesting, beautifully written. The one thing that is assumed on the part of the reader is some good background in manifold theory, because right off the bat you see some heavy use of at least notations in manifold theory, volume forms, and the Reimannian metric, in sense of having a dot product on the tangent space. Some of the results when I first read were not clear to me, but then it turned out that I had to begin with assuming that the Euclidean spaces are also manifolds and not fix any particular coordinate system from the beginning, because later, depending on what is needed, you choose the right coordinate system so that some of the formulas become simpler. So, as expected, these notes start by proving the Coarea formula for linear maps using Fubini's theorem, as you see in the computations in 1.3 here. And also you see the use of the volume form notation. Then comes some linear algebra, discussing why the Coarea factor for linear maps must be this particular determinant. One thing that we haven't covered is that this Jacobian is multiplication of the eigenvalues of A times A conjugate. And then there's a proof of this. And then there's another formula for the Jacobian, also the formula in terms of the Reimannian. We talked about a very similar formula to 1.6, and I also mentioned that this was covered in these notes. At least I hope I did. And there's also proof of this one. So that covers the linear algebra. Then we go to prove the Coarea formula for submersions. In our terminology, this would be the set where the rank is complete. And the proof is for the case where you have a simple map that is, so the last line in this page, you see that yj equals xj. So this is saying that the map is given by just a simple projection, like the simplest projection from larger Euclidean into the lower dimensional Euclidean space. And the proof uses all these linear algebra facts built earlier, so we end up proving that. And then comes this. So I'm looking for, okay, so the last line of this proof here, it says that the general case can be reduced to the specific case via partition of unity and the implicit function theorem. And here was where I was having some trouble, because we had to have this not so easy transformation formula chain rule for the Coarea factor. But using the language of manifold theory, this becomes kind of hidden into all of these dvy's and dvx's and dv fibers, and which is quite different from the way I was looking at it, because to me, I started with some coordinate system on my Euclidean spaces. Okay, so everything here is C1, maps between manifolds, and because of this, working with manifolds from the beginning, these results can be easily stated for manifolds, because we are treating Euclidean spaces also as manifolds after all. And then there are corollaries, how to compute volume by computing the perimeter of fibers up to the Coarea factor. Here you see this in the denominator. There's a discussion of how to get the volume formulas for spheres and balls by finding recursive formulas using the Coarea formula. But I would say this is also a consequence of Fubini's theorem, and we don't need the Coarea formula for this. So up to this point, someone only familiar with manifold theory can have a version of the Coarea formula that they can use. But then if you want to move into the Lipschitz world, you need to begin to talk about Hausdorff measures, because the pre-images are not manifolds for Lipschitz functions. You cannot integrate using the volume forms. You have to integrate using Hausdorff measures. So there's an introduction of Hausdorff measures, its basic properties. And then there's Eilenberg inequality. As I mentioned, there is no way you can prove Coarea formulas without this inequality, because it's used in the measurability of this function that you see in the last corollary. Then you go back to the manifolds, differentiable manifolds, and using this Coarea inequality, or a version of this, you prove this lemma for 2, which is our weak Sard's theorem. So the set where Jacobian is 0, the set where the rank of the derivative is less than n, picks up 0 sets from the fibers for almost every point in the image, and there's a proof of that using similar covering arguments that we had. Okay, so some more manifoldy stuff. Okay, and then there is the Coarea formula for Lipschitz map between manifolds, and here, because everything has been already done for C1 category, you can deduce everything from this C1 approximation of Lipschitz functions, that there is, for every Lipschitz functions, there is a C1 function which agrees with it, except on a set of measure less than epsilon. And the Eilenberg inequality takes care of small sets. Therefore, at any precision prescribed, we can ignore subsets, and then we have just the C1 world. And from the C1 versions of the theorems, we get the Lipschitz ones. As you can see here, there is this C epsilon removed from A, and the formula holds on C epsilon, and we let epsilon go to 0 to deduce that different approximations converge. Okay. So with this approach, the generalization to manifolds becomes easier. And in the last part, of course, there's introduction to what rectifiable sets are, and then the reduction of the deduction of formulas for maps between these, as you see in this Coarea formula final version. Again, in this case, rectifiable sets are Lipschitz images of subsets of Rn. So a map between rectifiable sets after you locally parameterize them is just, again, a map between honest Euclidean spaces. so the formulas follow. Okay, there are a few more things in these notes that I haven't touched up yet on, and they will occupy separate videos. So in that, because of that, I just skip commenting on things that we haven't even talked about. Thank you a lot. So please feel free to also use these notes if you want to add a different perspective to the Coarea formula. See you in my next video. Thank you so much again for watching. Have a great day.